Okay, guys. So right now, Mr. Varseller assigned us Biology Diffusion Part 1 and Part 2. Now this is going to be graded as an evidence next class. So I want to just go through the two that I just completed and hopefully explain it so that you understand, and hopefully you'll do a better job next time. So the first thing that you're going to want to do is grab a computer, or I'm going to use my iPad here. And what you're going to want to do is go to Explore Learning. Just type it in. Explore Learning. And here you want to sign in. I'm already signed in here. But here, let's just log out. And if you haven't already, type in your class code. Now, I'm going to show you the class code here. Leave it on the screen for a second. If you already didn't sign into it, you should have done it in class, but if you didn't, here's the class code. Pause the video if you like. There you go. And then you just type it in here. And then just type in your name and everything else. But, I already did it. And log in. Once you're logged in, you should already see right here, should say Bio Diffusion, and then launch gizmo. And then this gizmo should be launched. See multiple things here. You see description, table, bar chart, and the graph. And then all these weird, wacky lines here that you can change if you want. Now, once you have this all set, just set it aside for a minute. Don't really need it. And what you want to do, take out your paper. So take out your paper and just read it. So the first question is asking, describe the motion of gas particles. So now gas is just a normal fluid. And if you think about fluid like water, a fluid conforms to whatever shape it's in. Like if you pour water into a glass, the water in the glass, it doesn't stay how it was before. It conforms to the shape of the glass. That's the exact same thing that happens with gases. When you open up, let's say, a bottle of perfume, or you spray a bottle of perfume, the entire molecules of the perfume is going to try to permeate throughout the room. So let's say this is open here and it has some sort of opening. It will try to fill this opening so that this side and this side is about equal. So describing the motion, it's a random movement that tends towards equilibrium. So these random movements of the gas molecules bumping into each other, they tend to go towards an equilibrium. Next to, so now it's actually asking you to go onto the gizmo and like select the bar chart. So go to the gizmo and select the bar chart. Now once you're here at the bar chart, what you're going to want to do is set a couple of standards, because we want the variables, we only want them to be one changed variable. So the first thing you would want to do is reset. If you haven't already, it's already reset. And then set the wall to 100, just like that. And for this entire lab, what you're going to want to do is just change the temperature. That's all you're going to change. So start it off at 100. Now just press play really quickly. And now you see, you can kind of see that the gas molecules are moving, and they're moving fairly well, I would say. This isn't really changing. Now pause it, reset it, and move the temperature all the way to 6,000 or 600 Kelvin. Press play. They're moving pretty well. They're moving way quicker than they were before. So Kelvin, this is just the temperature. Higher the number, the higher the temperature. So you can kind of extrapolate from this that the higher the temperature, the more the particles move. As you can see, I wrote here, at 100K, the particles move slower than at 600. Now, why this is, if you imagine it, temperature is just a form of energy. And the more energy you put into something, the faster it'll move. So the molecules in the substance are vibrating faster, they're moving faster, so they'll diffuse faster. You can think of it of throwing a ball, just rolling it across the room, and then just chucking it across the room. Of course, the ball that you chuck is going to reach the end of the room faster. This is basically the same thing that happens with gas molecules. Now, after you wrote this, first two things down, you're going to actually go into the experiment. So what you're going to want to do is reset, and then put the temperature down to 100 Kelvin. And take the wall and set it to 50. And then A should be at 100. And if your graph, if this area looks like mine, you'll be good to go. Now, the first thing that you're going to want to do is change it to table, just so it's a little easier to see the numbers. And press play. Now, what you're going to look for is about when this percentage is 55% or lower. So we're looking 75, 74, 73. It's getting there. It's taking a little while, but it's getting there. 68, 67, 65. And once it reaches 55 or under, you're going to write it in this graph. As you can see, I already wrote it, but let's just see what this says, because numbers might be different. As with all experiments, you shouldn't get, it's ideal to get the same number, but you might not get it. 57, there you go, 55. So just pause it when you see a 55. And it's right here, 55. 55% in both of these at around 204 seconds. So take your paper and just write 204 there. And then you would reset and do the scan. You do this for a total of 5 times, and each time you would write it in your graph. After you do it for 5 times, you take the average of them, so add them all together, and divide by 5 to get your mean. So once you got your 5 scores, what you do, instead of taking it to 100 Kelvin, take it to 200, that's 205, 200, you get the idea. And then you would do it again, another 5 times. After that, 300, 400, 500, and eventually 600. And you would keep doing these 5 times, and then taking the average of those 5 times. You would make a graph on your table here, but I just wrote it on a flashcard, so it's easier for me and Mr. Varseller to see. You don't have to do it this way, I just did. And after you did all of this, you should begin to start seeing a trend, usually from the 100 to 200 Kelvin mark. And you would write that trend of here. You would write it right here. So, how did the temperature affect the movement or the rate of diffusion? Now, if you think about it, as I mentioned before, the temperature is just energy. So, the more energy you put in, the faster the molecules move. And using that, you would think the rate of diffusion would be faster. And that's true. As more energy is put into the molecules, the rate of diffusion is faster. After you come to that conclusion, you do number 4, you write down what you see, and then you would graph it. Now, I did it on the computer, and I printed it off. You don't have to do this by any means. Just take your points, so take your highest point, which for me was 350, and kind of make that in the range of what your highest y value will be. And then your lowest is about, mine is 100. Use that in consideration. So my scale should go for like 20s, so like 0, 20, 30, 40, 50, 60. 0, 20, 40, 60, 80, 100. You get it. And then for the temperature, it would just be 100 to 200, 300, 400, 600 Kelvin. And you would just graph this manually. Just take your point, plot it. So I would go at 100 Kelvin. I would be at 351. So I'll go at 351. Let's say like that's right about here. And then at 100 Kelvin, and I would make a point here. I'll make another point here, around here, 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 and here. And then I'll just take a ruler and graph it. You don't have to do this trend line as well. I just did it just because it's better. Shows a better picture of what's happening here. And that's just for diffusion part 1. I'll see you guys in part 2, where we're actually going to do our own experiment. Instead of changing the temperature, we can change whatever we want.